Yeah, so I'll be talking about this paper on high accuracy sampling from constrained spaces using the Metropolis-adjusted Preconditioned Langevin algorithm. And this is on behalf of Vishwak, Andre, and Ashia, who could not be here. So the task here is to sample from a constrained space. So sampling from a distribution whose support is constrained. In the previous talk, for example, we had the unconstrained setting. So this is common, once again, for like Bayesian modeling, differential privacy, querying a bounded feasible set, or randomized algorithms for volume computation. And more formally, the goal is to generate approximate samples from pi proportional to e to the minus f. And the support of this target distribution pi is a proper convex subset of RD. So classical algorithms for this task include hit and run, which picks a direction uniformly at random and then takes a step in that direction. The ball walk, which draws a ball around the current iterate and then moves to a step in the ball. And then the Dickin walk, which considers a Dickin ellipsoid centered at your current point and then moves to a point in the ellipsoid. This work approaches this question from the lens of optimization. So what do we usually do in constrained optimization? So suppose we have our goal is to minimize a convex function f supported on k. We identify a mirror function phi over k, which is of Legendre type. And we can then have the mirror flow ODE, discretizing which gives us the mirror descent algorithm, which is very popular in optimization. This is equivalent to the natural gradient flow with metric given by the Hessian of phi. And the question here is, what is the equivalent analog of the mirror ODE and the natural gradient flow ODE for sampling? So for sampling, we have the goal of getting a sample from pi proportional to e to the minus f, and the mirror Langevin dynamics is this following stochastic differential equation. If you remove the orange part here, you get exactly the mirror flow ODE. And the Fokker-Planck equation describes the update of the density. So it's a PDE where rho t is the law of xt. And as xt evolves along this, rho t evolves along the Fokker-Planck equation. Now, given this Fokker-Planck equation, you can ask what happens if you plug in a different metric here. So this is explicitly for the Hessian metric. But you can consider the weighted Langevin dynamics, where you are plugging in some general metric g. And this is equivalent to this update in the space of random variables. Right, and this is the natural gradient. And once again, if you omit the red stuff, you get the natural flow, gradient flow. But again, once again, this is all in discrete time, so we need to discretize in time to get algorithms. So the simplest discretization is the forward Euler method, similar to what the ULA was for Langevin dynamics in unconstrained space. So the mirror Langevin algorithm is the following update. And if you skip the orange part, then you get the mirror algorithm for optimization. And this is the weighted Langevin algorithm. So this is just both of them written again. And then if we compare these two, there are a few things that we need to check. So firstly, are they feasible in that does the next iterate stay within our feasibility set k? For the mirror Langevin algorithm, it does stay in k because the update is actually happening in the dual space, which is unconstrained, and then we are mirroring back to the constrained space. So it is bound to stay in k. For WLA, however, that is not guaranteed because xk plus 1, there is this, we are adding a Gaussian random variable here, which can very well push us outside our set. And in terms of computation, for MLA, we need the gradient of the convex conjugate of phi. And for WLA, we need the divergence of G inverse. These are the additional things we need over and above the more classical assumptions of first order and second order access to phi. And neither of these are unbiased, so they both have different distributions as the stationary distribution. So the main observation here is, what if we removed this problematic divergence term in the WLA? What is the algorithm that we get, and can we actually use it for sampling? This gives rise to the PLA, and this is nothing but the WLA, but without the problematic divergence term. And while it is still not feasible and it is not unbiased, there is no overhead in terms of computation that you need to implement it. So now the main two issues that we need to talk about are the feasibility issue and the bias issue. We can address both of these by considering a Metropolis-Hastings filter applied to the proposal given by PLA. So this gives rise to a Markov chain, say, called MAPLA. And so recall what the Metropolis-Hastings filter says. So suppose you have a Markov chain P, which is the collection of pointwise distributions, which is telling you if you're at point X, where do you go next? The proposal distribution, this like family collection of PX for PLA is given by this explicit Gaussian density. And the Metropolis-Hastings filter accepts a proposal from this Markov chain with some probability given by the minimum of 1 and this ratio. Note that this ratio is easy to compute in the setting of PLA because this is exactly Gaussian. And this was motivated by prior work at Colt on adding a Metropolis-Hastings filter for the Markov chain induced by the mirror Langevin algorithm. And here for MAPLA, the key features are that there is no need to compute the gradient of phi star, which you would need for Metropolis-adjusted MLA. And it also extends beyond compact supported distributions. So theoretical properties of MAPLA are as follows. So there is asymptotic convergence to the target pi, so it is unbiased. And for non-asymptotic finite time guarantees, we need to place some assumptions on the potential F and the metric G. So we assume some curvature bounds on F, a gradient bound for F, and that G satisfies strong notions of self-concordance. And under these assumptions, the mixing time of MAPLA is given as follows. This is in TV distance. And there is log 1 over epsilon dependence on the error epsilon, so it is a high accuracy sampler. And there is linear dependence on the dimension D. The proof technique is conductance based, so you need to show a one-step overlap plus Cheeger isoperimetry. The properties of G and the curvature upper bound and gradient bound gives the one-step overlap conditioned. And the self-concordance assumptions plus the curvature lower bound yields a Cheeger isoperimetry. And this is all also extendable to the weakly log concave case, so where mu is 0, and for just self-concordant metrics, and that's mentioned in the paper. So a quick summary, methods from constrained optimization can be used to design algorithms for constrained sampling. It requires translating optimization to sampling, and here we translate natural gradient-based optimization of a function to natural gradient-based optimization of a functional. And more generally, we can take a bias method like MLA, WLA, or PLA and debias it with the Metropolis-Hastings filter. And this results in implementable methods with strong guarantees. Thank you, and please reach out to Vishwak for questions or comments.
Are there any easy questions about this topic? I'll ask, I guess, implementable. Do you know if they implemented it?
I think they did. So in the paper on arXiv, there are some experiments.
Cool. Okay. More easy questions?
Okay.
Miraculously,
Okay.
we're ahead of schedule.
Okay, thank you.